Mars rover suspension system. The Momentums. Mechanical design. Fall 2017. Project number 3. Table of contents. Introduction. Assumptions. Free body diagram. Hand calculations. Optimization. And conclusion. Introduction. In this project, we must design, analyze, and optimize the suspension system of a Mars rover. The rover must have a suspension system that has the ability to resist static and fatigue failure. Assumptions. The tube will not deflect. Only bending stress occurs. A small strain is to be assumed. The angle between the shock and the tube will not change. Temperature change will be neglected. Knowns. Design life cycles. Fatigue safety factor. Maximum loading and minimum loading. Distance where loading is applied. Length of hollow tube. Free body diagram. Reaction forces on pin A. RAX, RAY. Length of the tube 12 inches. Reactions on pin B, RBY. Distance from point B to loading 4 inches. Angle of loading 75 degrees. Unknowns. Diameter and thickness of hollow tube. Reaction forces. Moment of inertia. Maximum stress. Unmodified endurance limit. Factors of K. Modified endurance limit. Stress amplitude. Mean stress. Cycles of life. F factor and A and B constants for cycles of life. Hand calculations. Pmax is equal to 850 pounds of force at an angle of 75 degrees. The vertical component is equal to 821.03 pounds of force. When taking the summation of the moments with respect to pin A equal to 0, the reaction force in the vertical direction B is equal to 547.35 pounds of force. The reaction in point A then is equal to 273.67 pounds of force. The maximum moment is then found to be at 8 inches away from pin A and is equal to 2189.4 pounds per inch. Moment of inertia and maximum moment are to be found. Shear force and moment diagrams. On the left, shear force diagram showing a maximum shear of 273.68 and a minimum shear force of 547.35. On the right side, bending moment showing a maximum moment of 2189.4 pounds per inch. Equations to solve for maximum stress. Unmodified endurance limit. Stress mean, stress amplitude. Modified endurance limit. And safety factor. Excel calculations process of optimization. After several hand calculations, the team decided to use all of the available dimensions found in Appendix A8, and the following table was produced. The optimum dimensions to meet a safety factor of equal or greater than 3 are outer diameter 1.5, thickness 1/4 of an inch, yielding a safety factor of 4.22. The exact dimensions to achieve a safety factor of 3 are outer diameter 1.5, thickness of 1/7 of an inch, yielding a safety factor of 3.000. As previously mentioned, the dimensions of 1.5 inch by 1/4 thickness are found in Appendix A8. These dimensions will yield a safety factor of 4.2, meeting the requirement of a safety factor of 3.
Hand calculations. These hand calculations show the process to find the safety factor and the cycles to failure. On the left side, the process to find the safety factor is shown. By finding the maximum stress, the stress mean, the stress amplitude, the unmodified endurance limit, the K factors, and the modified endurance limit. In the case shown, the safety factor equals to 20.189, approximately 6 times larger than the necessary safety factor. On the right side, the cycles of failure equal to 0.417 times 10 to the 9 cycles. Finite element analysis. The team decided to further investigate the hollow tube's dimensions by modeling it in a finite element analysis software, as shown in the picture. Optimization. It's shown on the Excel calculations how the design was optimized numerically. The last row of the Excel chart shows the dimensions will meet the safety factor of 3 to the thousands. Conclusion. The project was completed by examination, utilizing all of the dimensions found in Appendix 8.8. The objective of this project was to find the dimensions of a standard hollow tube that will meet the required safety factor of 3. The team decided to choose the dimensions of 1.5 inch diameter by 1/4 inch thickness. These dimensions will yield a safety factor of 4.22. The dimensions of the hollow tube are reasonable, since the tube size is comparable to the size of a tube found in a common car. In comparison to a pickup, the suspension tube of a pickup is under a force of approximately 1,000 pounds force, determined by mass distribution. The hollow tube with the chosen dimensions is under a force of only 850 pounds force. The tube has appropriate dimensions for the application in comparison to the pickup. Furthermore, optimization allowed to discover the dimensions of 1.5 inch diameter and 1/7 of an inch thickness will yield a factor of safety of exactly 3. However, these dimensions will reduce weight. The cost of manufacturing might be higher since more precision and accuracy equipment must be used, for example, in CNC machinery.